Hey guys, I'm going to go over the 7.6 and 7 through 7.8 homework. And if you're wondering what happened to 7.5, 7.5 is for BC only, and so 7.9. So those two sections I'm going to cover on a different day for BC. But in these sections, we go over solving differential equations, which is pretty much just using antiderivatives. So, and many of these equations are going to be separable, meaning that you want to separate the variables of x and y. And so I think that's what I'm just going to try here. I'm going to try and separate the x and the y's. And so what I think I can do, I actually don't need any separating here except for the dx. The dx should come over here, but 1 over the natural log of 2 is just a constant, and then 1 over x is the function. And since there's no variables of y over here, I don't think I really need to do much else. So the only thing is just to multiply both sides by dx. And so dy will equal 1 over, now I am going to say 1 over the natural log of 2. No, I'm not. I'm trying to think of the best way I want to do this to anti-differentiate, but okay, I'll just do 1 over x natural log of 2. Just keep in mind that this is just a constant. It's no different if this was 1 over 3x or 1 over 4x or something like that. It should just be used as a constant. Okay, and then times by dx. And then we're going to integrate both sides. Obviously, if we integrate here, we'll get y, because there's it's just 1 dy, so we'll integrate, we'll get y equal to, now the antiderivative of 1 over x is going to be the natural log of, that's just going to be the natural log of x, right? The antiderivative. So it's going to be the natural log of x. It's going to be natural log of x, and then that constant is just going to be, there, divided by the natural log of 2. And that's it. Plus c. So the natural log of x divided by the natural log of 2. So that should be a. Don't forget that you could always just check your answer. The derivative of the natural log of x is 1 over x, and since this is a constant, 1 over the natural log of 2 is the constant. It would make sense that that's what it would become. So, okay, there's 1. What is the general solution to the differential equation given here? So now in this case we have both, this is defined in both x and y terms, and so I'm going to separate these variables by multiplying cosine of y over here and dx over there to separate those variables. And so we'll have cosine of y dy equal to cosine of x times by e to the sine of x dx, and then we're going to integrate. So what's the antiderivative here? The antiderivative of cosine of y would be sine of y. That's going to be sine of y equal to, now notice that we have a product here. We have a product. And just remember, hopefully you learned this from the test, that we don't just do the antiderivative of one times the antiderivative of the other, but a product can be dealt with in an integral either by simplifying or one of the special techniques. In this case, it's going to be one of the special techniques. This one's pretty obvious because we know that the derivative of e to the sine x, this would have to be integration through substitution, but I don't actually have to use substitution. I can pretty clearly see that the antiderivative is e to the sine x plus c. And that's because if I take the derivative of e to the sine x, that's going to be e to the sine x, but then through the chain rule, you'd also have to multiply by the derivative of sine x, which is cosine of x, and that's what I have right here. So here's our antiderivative on the right side, and now I have to solve for y, which means I would use an arc sine. So y would be equal to arc sine of e to the sine x plus c. And yes, the c, the constant, does matter where the constant is. And so arc sine, so that should be b right here. For 3, what is the general solution? So a lot of these have said general solution, what are all the solutions? This just means that it should include the plus c whenever we anti-differentiate. So I'm going to separate the variables. So I'm going to multiply by 3y squared. So 3y squared dy should be equal to x minus 1 dx. And then I'll anti-differentiate. The antiderivative on this side should just be y cubed, right? And that will be equal to 1/2 x squared minus x plus c. And then I'm going to use the cube root on everything. So cube root and cube root. So y will be equal to the cube root of 1/2 x squared minus x plus c. So that's going to come to be d. For 4, what are all the solutions to the differential equations here? Oh, this one's easy. You can multiply by dx here, and then you'll have dy alone by itself, and the antiderivative of dy will just be y. And then the antiderivative of secant squared of x is a tangent of x. That's an easy one. So there you go. For 5, what is the general solution here? So let me separate the variables. So I'll multiply by 4y. So 4y dy will be equal to x times by cosine of x squared dx. The antiderivative here should be, 2y squared? Yeah? Equal to, this is going to be an easy u sub or a chain rule. So just think about the chain rule. The derivative of the inside part is 2x, which is the same as what's happening outside here. Should I just go through the process, or should I try and piece it together without having to do much? It would have to be sine of x squared, right? So it would have to be, sorry, let me put that in there. It's going to have to be sine of x squared plus c. So let me first check this right here. So if I do the derivative of sine is cosine of x squared, but then I would have to multiply by the derivative of the inside, which would be 2x, which is why I have the x here. But it does mean that I'd also have to divide this by 2 because there is no 2 here. So I think I'll do this as 1/2 sine of x squared. So let's double check now. So I would have 1/2 if I'm taking the derivative of this in hopes to get the same thing here. So I would have 1/2 times by cosine of x squared, because cosine is the derivative of sine. Then I'd have to multiply by 2x for the derivative of the inside, and the 2's would cancel, leaving me with x times by cosine of x squared, which is what I have up there. Perfect. And then I'm going to have to divide both sides by 2. So if I divide by 2, I get y squared is equal to 1/4 sine of x squared. Now you might say, shouldn't I also divide this by 2? Sure, but that doesn't change the fact that c is any constant. And then if I divide any constant by 2, it still leaves c to be possible to be any constant, and so it doesn't really matter. And then I'll take the square root, and I'll get y is equal to the square root of 1/4 sine of x squared plus c. So I think that's got to be B. All right, for 6, sorry, it's happening on 2 pages. All right, so this one's actually kind of tricky, it looks like. You can see here, so we have a square root of y on both of these. So this is kind of where they do start to get tricky. This one's actually not too bad. There's definitely more tricky separable differential equations, which I'm sure we'll come across. But in this case, the tricky part to know what to do here is just to factor out the square root of y. So I'll get dy dx is equal to the square root of y, and then I'll get 1 minus sine of x. And now this is where I can separate them. So I can divide by the square root of y on both sides, and then I can multiply by dx to both sides. So I'll get 1 over the square root of y dy whenever I divide both sides by the square root of y. Now I'm just going to take some time here to rewrite this expression. I can rewrite that as y to the negative 1/2. Okay, and so that's going to be equal to 1 minus sine of x dx. And then let's go ahead, since I've separated the variables, I can anti-differentiate. Here, that's going to be y to the 1/2 times by 2, I believe. Yeah. And then that's going to be equal to x minus, would it be plus cosine? Plus cosine of x, right? Plus cosine. So the derivative of x is 1, derivative of cosine of x is negative sine of x, okay? And then plus c. I'll divide everything by 2. So then I'll get, I'm trying to see how the answers are written, and they don't have it all divided by 2. So I don't think I'll do that. So I'll just do 1/2 x plus 1/2 cosine of x plus c. Actually, what they do instead is they just have the constant on the outside. So let me go ahead and do that. So it's just going to be 1/2 and then x plus cosine of x plus c. And then take the square root. Y is equal to the square root of, I'm not getting the same thing at all over here, am I? So what did I do wrong? Oh, that's because I'm not square rooting, am I? I'm supposed to be squaring. That's why. Duh. So I should square all this. So whenever I square that, that's going to become 1/4. That's right. And then I'll have x plus cosine of x plus c squared, which will be d. There we go. All right, for 7, which of the following solutions to the differential equation dy dx with the initial condition? Okay, so this one, in these problems, we're not solving for a general solution. We're actually solving for a particular solution, and so that's why they give us an initial condition. So this is not a whole lot of space to work with. We'll make do. So let's separate the variables though. So I do have a y minus 2. Let me go ahead and move that over here along with moving dx over here. In order to save some room, I'm going to write above it. So y minus 2 times by dy, that will be equal to x minus 2 times by dx. And then we will anti-differentiate these. Good thing is that the antiderivative will be the same. Just with different variables. So if we are anti-differentiating this, that's going to be 1/2 y squared minus 2y. Okay. That, I don't like that too much. Oh, wait a minute. I did something wrong here. Hold on. I divided by y minus 2, so that should be 1 over y minus 2 dy equal to x minus 2 dx. Okay, that looks a lot better. The last one, what I had written before, was not looking good in terms of solving for y. This is much easier because the antiderivative of this, if I have a constant over a linear factor, the antiderivative is the natural log y minus 2, and then that will be equal to 1/2 x squared minus 2x plus c. Can't forget this right there, right? Okay, all right, so now we have a couple options. What we can do is we can use our initial condition right here and plug it in and solve for c. Then I can solve for y, or I can solve for y, then plug in the initial condition. Really, this doesn't matter too much, but typically I'm a guy that likes to plug this in and then I'll solve for y later. And so I think that's what I'm going to do. So I'm going to plug in 5 for y. So that's going to be the natural log of 3 equal to, and then I'm going to plug in 4 for x. So 4 squared is 16 divided by 2 is 8. And then if I plug in 4 here, that's going to be minus 8. So that just means that the constant c is going to be equal to natural log of 3. So that's going to be equal to c. Now, just a heads up. If you decide to solve for y and then you decide to solve for c, you might not get the same constant, which is weird. But there's a good reason for that. But it will give you, either way, through simplifying, you'll get the same answer that we end up with. And so maybe I can highlight that here. That actually might be a good idea, and I'm not sure if I'm going to show that in class. But so let's just say that I plug this in as the natural log of 3 for c right here. So the natural log of y minus 2 equal to 1/2 x squared minus 2x plus the natural log of 3. Okay, now the next thing that I'm going to do is exponentiate with a base of e on both sides. So then when I do that, I'll get y minus 2 equal to. Now, this is all the exponent of e, and there's a property of exponents. So if I have e to the x plus y plus z, this is equivalent to e to the x times by e to the y times by e to the z, because when I have the same base, if powers have the same base and you're multiplying them, you can add the exponents. So you can use it in either way. So I know you guys are familiar with that. So that's what I'm going to do here, except I'm going to, so these 3 terms are being added. So I could technically write this as e to the 1/2 x squared times by e to the negative 2x times by e to the natural log of 3. However, I'm not going to do it quite like that. Instead, what I'm going to do is I'm going to write it as e to the 1/2 x squared minus 2x, and then times by e to the natural log of 3. Now, the reason why I would do that is because this is a natural log and this is a base e, kind of the same thing here. That's going to cancel, and this coefficient is just going to be 3. So this is going to be times by 3. And so then I'll get y is equal to 3 times by e to the 1/2 x squared minus 2x plus 2. So then that will give me the answer of B. Okay. Now I'm gonna go back over here. If you guys don't care to follow me on this right here, that's totally fine. But let me just show you how that might have looked differently if we chose to solve for y first. So the first thing I would do here if I'm solving for y would be to use a base e first. So then if I do that, I'll get y minus 2 is equal to, and I'm going to use the same thing that I did in this step right here. If I'm using an e here, so if I do e, if I exponentiate, Yeah, no, yeah, I'm going to do the same thing here. Or am I? Yeah, sure. So e to the 1/2 x squared minus 2x times by e to the c power. You can tell that I don't often do it this way, huh? And then we're going to add 2. And now what we're going to do, yeah. You know what, I don't think I had to do the times by that, although I think that's what's going to happen. I'm just going to say plus c here. Yeah, but I still think it's all going to be the same. So let's go ahead and plug in our initial condition now. So if I plug in the initial condition, I'll get 5 is equal to e to the 1/2. Now let's just go ahead and plug in 4 right here. So if I plug in 4 squared is 16, divided by 2 is going to be 8. And then if I plug in 4 here, it's going to be minus 8. So it's just going to become, yeah, e to the c plus 2. Yeah, okay. And then we'll subtract 2. So I'll get 3 is equal to e to the c. And then I'll use I do get the same thing, don't I? So I'll use the natural log. I'll get the natural log of 3 equal to c. And then I'll plug that in back up here. So then I would get y is equal to e to the 1/2 x squared minus 2x plus the natural log of 3 plus 2. And that's where, so you notice that this answer isn't written over here. That's because in this answer right here, they don't have the natural log of 3, because if you have e to that base, it becomes just 3, which is why they have the constant here instead. So I just wanted to take time to explain that if you did do it this way, this is how you would manipulate it to get this answer right here. On a free response question, there's no problem with leaving it like this right here, though. Remember that on a free response question, you don't have to simplify. And if you do simplify and simplify wrong, you get the answer wrong. But just kind of explain the difference between the choices here. Okay, 8. Okay, so we need to separate the variables. Similarly with what happened up here, we have to group up the y's. So keep in mind that you can write this as y squared minus x squared times by y squared. And by writing it like that, it allows you to factor out the y squared and then divide by it. And so that's what I'm doing. I'm going to do my first step. I'm also going to multiply the dx over there. So I'll get dy is equal to y squared 1 minus x squared dx, and then I'll divide by y squared, so I'll get 1 over y squared dy. However, I'm not going to keep it like that. I'm going to write it as y to the negative 2 dy equal to 1 minus x squared dx. Okay, and then let's see, give me some room right here. Okay, and then let's anti-differentiate. So then I'll get negative 1 over y, I think, so you'll have to add 1, which will be negative 1, which is why I'm putting it in the denominator, and then you have to divide by negative 1, so I think that's good. Equal to x minus 1/3 x cubed plus c. I think that's right. Let's go with it. Alright. Solving for y is going to be a bit of a pain. So I'm gonna plug in my initial condition and solve for c first, though. So let me take some time to do that. So if I plug in 1 for y, that's going to become negative 1 equal to 3 minus 1/3 times by 27 plus c. So negative 1 is going to be equal to 3 minus, what is that, 9 plus c. So negative 1 is going to be equal to negative 6 plus c. So c should be equal to 5. So c should be equal to 5. Okay, and then this will be negative 1 over y equal to x minus x cubed over 3 plus 5. Okay, so here's how I'm going to solve for y. I'm going to get a common denominator here, because if I make this into a fraction, just like something like right now I just have this as a fraction. So I'm going to get a common denominator, which will allow me to just use the reciprocal of these sides right here. So negative 1 over y is going to be equal to, so 3x, because I'm going to multiply this by 3 and multiply that by 3 to get a common denominator of 3. So minus x to the third plus 15 all over 3. And now I can just use the reciprocal, or cross multiplication, however you guys want to call it. So I get negative y will be equal to 3 over am I doing this right? 3 over 3x minus x to the third plus 15, and then I'd obviously have to multiply by negative, so I'll get y is equal to, I'm trying to see which one, so I think they're using b as the answer, and so the negative, yep, so negative 3 over 3x minus x to the third plus 15, and there we go. Okay. That's how I would solve for y there. Get a common denominator because y is in the denominator here, which just allows me to flip the fraction to solve for y. Much easier to kind of do it that way. If you have one rational expression rather than 3 distinct terms, get it into one rational expression to match that. Alright, for 9, let's see, let y equal f of x be the particular solution to the differential equation with the initial condition here. Which of the following gives the expression for f of x and its domain? Okay, so let's go ahead and separate the variables. So you might be asking yourself, how the heck do I separate the variables? Something that is going to feel like the right thing to do, but is the wrong thing to do, would be to minus y squared. You do not want to do this in this problem. So if I do that, if I subtract y squared, let me do this in red. If I subtract y squared, I'll get dy dx. It depends. So you can write it as negative y squared, but it's going to be plus dy dx. It's not going to be multiplication. And that's exactly what we want. We want it to be times by dy, times by dx, times by dy, times by dx. Adding dy and dx is not what we want here. Not at all. And not only that, but on the other side, that would leave us with 0. And so then trying to separate dx over here from all of this right here, so say that I tried to do that, well, in order to get rid of dx here, I would have to multiply by dx to get rid of the dx here, but that would also give a dx here, which would be mixing variables again. So I think, I don't know, maybe you can work it out to get to that, to get to the same thing, but it would require a little bit more math and algebra, and it also just might lead you to a situation where you don't know what to do and you give up. And so rather what you want to do, it's just there's nothing wrong with just dividing by y squared here. So just divide by y squared and multiply by dx. There's absolutely nothing wrong with that. So if I divide by y squared, I'll get 1 over y squared dy. But again, I don't like writing it like that when I anti-differentiate, so I'm going to say y to the negative 2 dy equal to, now if I divide by y squared, that leaves me with 1 over here, not 0, it leaves me with 1, and then I'm multiplying by dx, and so that's all it's going to be over here, it's just going to be 1 dx. This is what I want. And so I can anti-differentiate. Remember that over here, I'm basically just anti-differentiating 1, which becomes x. And the antiderivative here is negative 1 over y equal to x plus c. So you see there, it's actually really easy that way. So that's the other part about separable differential equations, is that sometimes all you really need to do is just divide by whatever you need. Don't add or subtract those terms. Really is not too helpful when you do that. So as for the initial condition, so negative 1 is equal to 1 plus c. Subtract 1 and subtract 1, and you get c is equal to negative 2. So I get negative 1 over y equal to x minus 2. And then this is all over 1, which allows me to kind of do the same thing here. I can just flip it, so I'll get negative y is equal to 1 over x minus 2. And then you can say that y is equal to negative 1 over x minus 2. Let's see what they did. I do see here that the order that these are in are reversed, meaning that they put the negative in the denominator. So 1 over 2 minus x, 1 over 2 minus x, and x cannot be equal to 2. So that's got to be, oh man, hold up. Wait a minute. This right here is a rational function. So we don't just want, so the rational function has two branches. It's going to have a branch on this side and one on this side of x equals 2, because there's a vertical asymptote at x equals 2. And so with that being said, we only want to contain, let's see, how do I want to say this? I only want to include one of the branches. It's kind of weird how that works out with x cannot be equal to, no, x cannot be equal to 2. So I'm trying to visualize this graph right here. So I think it should look something like this right here. Yeah. So we want it, this is what it's going to look like. Now, it really depends on the initial condition as to which branch you want to include for the solution here. So the initial condition says that x equals 1. Well, that's going to be on the left side of the branch, and that's going to be when x is less than 2. And so the answer has to be D right here. So it's kind of weird how these rational functions work out in terms of solutions to differential equations, but the domain depends on if there are multiple branches in if there are multiple branches of the function, like a rational function. If a function has multiple branches for differential equations, then only do the branch that is included in the with the initial condition. So that's when x is less than 2, since 1 is included in that part right there. Okay. All right. Let's see. So for 10, all right. During optimal conditions, the rate of change of population of a certain organism is proportional. All right, so keep that in mind, proportional. This is kind of going back to our first sections in this one. So during optimal conditions, the rate of change of the population of a certain organism is proportional to the population at time t in hours. At time t equals 0 hours, the population is 300. At time t equals 24, the population is 1,000. At what time is the population 500? So this is referring to different exponential differential equations. So exponential differential equations. And exponential differential equations are dy dx is equal to k times by y, and they have a solution of y is equal to some constant e to the kt, remembering that c is the initial value. Kind of like PERT. It is PERT. So in any case, so let me go back and get some information. The rate of change of population is of a certain organism is proportional to the population. So there's our hint that it's exponential. So there's a population, and the rate of change, it's proportional to the population. It's proportional to itself. K times by y. It's proportional to whatever we are actually measuring the rate of change with. At t equals 0, the population is 300. Therefore, c has to be equal to 300. Okay, at 24 hours, t equals 24, the population is 1,000. So the population is going to be 1,000. That's going to be equal to 300 e to the k times by 24. So the objective, what is the time when the population is 500? Oh my gosh, they're having us do so much stuff here. The population is 1,000. What is the time when the population is 500? And so in this case right here, we're going to solve for the constant k. That's what we're missing. And then we're going to make one more equation where we can substitute 500 for the population. Yeah, so let me walk you through what I'm thinking. So we'll divide by 300. That will give us 10 over 3. So divide by 300. We'll get 10 over 3 equal to e to the 24k. And then we'll use the natural log on both sides. So I'll get the natural log of 10 thirds equal to 24k. And therefore k will be equal to the natural log of 10 over 3 divided by 24. Okay, and now let's find the time when the population is 500. So 500 will be equal to 300. Note that this is always going to be 300 because that's the initial condition. Doesn't matter what the population ends up being, whether it be 1,000 or 500. So then e to the k, and that k is the natural log of 10 thirds divided by 24t. It's a very nasty k to keep like that, but that's what we're doing. And then we're just going to solve for t. So what is the time of the population? What is the time? At what time is the population 500? So divide by 300. We'll get 5 thirds is equal to e to the natural log of 10 over 3 divided by 24 t times by t. Then we'll use the natural log and the natural log. So this looks terrible. T is equal to the natural log of 5 thirds, but I can already tell that the answer is D because that's what it's going to turn out to be. So 5 thirds, and then that's going to be equal to the natural log of 10 over 3 divided by 24t. And there you go. You'll divide by all of this right here, which is why you have that all in the denominator there. So it's going to be D. All right, so for 11, so again, this is just following along the lines of exponential differential equations. A dose of 400 milligrams of a drug is administered to a patient. The amount of the drug in milligrams in the person's bloodstream at time t in hours is given by A of t. The rate at which the drug leaves the bloodstream can be modeled by the differential equation here. This is an exponential because you can see that it's proportional to itself right there. That's what we're looking for. Those are the same variables, so that means that it's proportional to itself. What type of equations are proportional to themselves? Exponential equations. Where k is a constant, which of the following could be an expression of A of t? So A of t would have to be equal to, notice here, that they do give us some information. They say that a dose of 400 is what's administered at the time. So I know that the initial condition is going to be for 400. And so if I simply look at these right here, that's not exponential, that's linear. This is quadratic, that's linear. This is exponential, but definitely not with the initial condition of 400. It's the initial condition here, it would be 1, I guess, and then it would just be plus 399. But yeah, it's got to be A. And so, yeah. You can check that. Let's see, how can you check the constant though? So you know that dA dt is equal to k times by A. Is there anything I can do to plug in? To solve for k to confirm that that's what it would be. Do I have any other information here? I don't think it matters. I can already tell that this is exponential. It's got the initial condition of 400. And so, yeah, it's got to be A. All right, so for 12, we'll need a calculator. The quantity R in grams of a certain radioactive substance decreases. K's got to be negative. Decreases according to the exponential decay model given here. So, yep, K is negative, where T is measured in seconds. During an experiment, the scientist determines that the rate of decay of a second substance with quantity S in grams can be represented by the linear model here, where T is measured in seconds. If at time t equals 0, R of 0 is 100 and S of 0 is 125, at what time in seconds will there be equal quantities of both substances? Okay, so let's see here. At what time will quantities, so that means R and S. When will R be equal to S, I think is what it's saying, which is probably why it's a calculator question. You're trying to figure out where R and S are going to be equal to each other. So R is an exponential equation. So, and we have this here. We also have the constant right here. So I can say R of t is equal to 100 times by e to the negative 0.05 t. This is the constant because I can tell from the differential equation given to us. So that's R of t. Okay. Now, how can I define S of t? Well, S of t is a linear model, and the derivative of S of t is given there. So S of t is going to be equal to negative 4t, and then the initial condition is 125, so plus 125. So we have the linear model with the derivative of negative 4. We have the exponential model with the initial condition of 100 and a constant as negative 0.5. And we want to see when these are equal to each other. So if you guys don't mind, I'm going to use Desmos. Just so much easier to use. Okay, so let's see here. We have, what was it? It was like 100, and then e raised to the negative 0.05x, and then the linear model was negative 4x plus 125. Oops. So that's when t is equal to 30. 30.7. Yeah, that's not any of our answers, is it? Oh, that's why. 100. 23.5. 20. There we go. C is the answer. Okay. 13. A kitten weighs 85 grams at birth. During the first 4 weeks after a kitten's birth, its weight in grams is given by a function W that satisfies this initial condition. So that means it's an exponential as its solution, where t is measured in days and k in some positive constant. Which of the following could be an expression for W of t? That's got to be A right there. So it initially weighs 85 right there. And then that's the only exponential equation that would match that right there. So, okay, 14. I think this is going to be very similar to this one up here, but let's give it a shot. So, extreme heat applied to a colony of microorganisms caused the size P of the colony, measured in grams, to decrease according to the exponential decay model. So you know that k is going to be equal to negative 0.4. Okay, the size of Q decreases at a constant rate of 1 gram per hour. Constant rate of 1 gram per hour according to the linear model. So you know that Q so far is going to be equal to negative t plus 3. And we know that P of t is going to be equal to, is our initial condition? Yeah, it's going to be equal to 2e to the negative 0.4 t. So that's what we're going to graph. So that's going to be negative x plus 3, and then it was like 2e raised to the, I don't want to mess up like last time, negative 0.4 x. And we have at 2.155, 2.156, so gotta be C. Okay, I know that one was a bit of a longer one, but it's good practice. A lot of times you'll see these questions on the free response often, so okay.